to the lecture series on differential equations for undergraduate students. Today's topic is partial differential equations. Like ordinary differential equations, partial differential equations are also equations in which is to be solved for unknown quantity, and the unknown quantity here is also a function. But unlike ordinary differential equations, here the unknown function could be of more than one variable, and the equation could be a relationship between that unknown function and its partial differentiation. So, we could define that partial differential equation as a partial differential equation is an equation involving a function u of several variables and its partial derivatives with respect to those independent variables. So, as in the ordinary differential equations, we were having a function, unknown function, which we had denoted by y, and one variable that we denoted by x. Here we may have more than one independent variables, that is, now we will denote those independent variables as x, y and t, so on, and the unknown function as u. Let us see some examples of partial differential equations. Say del u bar del x is equal to del u by del t, u times del u by del x minus del u by del t is equal to 0, e to the power x times del u by del x plus 4 times del u by del t is equal to t, 1 upon x del u upon del x plus del 2 u upon del x 2 minus del 2 u upon del t 2 is equal to x square, del 2 u over del x 2 minus e to the power 2 x del 2 u upon del t 2 is equal to u cube. So, you see here is in all these equations the unknown function is u. In the first equation, this is u is a function of two variables x and t, and we do have a relationship with the partial derivatives with respect to x and with respect to t. Similarly, here also, this is also an unknown function is of the two variables x and t. This last equation is also known as one dimensional wave equation. Then we do have del u upon del t is equal to c square times del 2 u over del x 2. This is known as one dimensional heat equation. Another equation known as del 2 u upon del x 2 plus del 2 u upon del y 2 is equal to 0. You see here the independent variables are x and y and the unknown function is u. This is known as the two dimensional Laplace equation. Del 2 u over del x 2 plus del 2 u over del y 2 is equal to a function of x and y. This is known as two dimensional Poisson equation. You see here is the differences, that is, here is the right hand side is 0, here is a function of x and y. This function is a known function. Another example is del 2 u upon del t 2 is equal to c square times del 2 u upon del x 2 plus del 2 u upon del y 2. This is two dimensional wave equation. This is not one dimensional, this is two dimensional. You see here the unknown function u is of the three variables x, y and t, and we do have partial derivatives with respect to t, x and y. Then we do have del 2 u over del x 2 plus del 2 u over del y 2 plus del 2 u over del z 2 is equal to 0. This is actually three dimensional Laplace equation. Here we do have three variables x, y and z. In all these equations, wherever we have used this c, that was used as a constant, that is a constant, and we had used the variables as one variable as t, another variables as x, y and z. So, this variable t is referred as time, and this x, y, z, they are nothing but the Cartesian coordinates, and you see sometimes we said is one dimensional equation and the times we said is two dimensional or three dimensional. They are because of these how many variables of this Cartesian coordinates we are having. As here we are having two Cartesian coordinates x and y, we call it two dimensional. Here we are having is x, y and z, so we call it three dimensional. Whenever we are having is del u x plus del u del u over del x plus del u over del t is equal to c kind of equation. There we had only x and t, that is one dimensional we are calling it. All these equations which I have shown you here as an example, they are of special importance in the partial differential equations. That is why here I have just given a little bit insight of those kind of equations. Let us understand some more basic terms and concepts in the partial differential equation. It is similar to the ordinary differential equations, but some more concepts we would be requiring. So, basic concepts. First is order. As in the ordinary differential equations, we define the order of a differential equation as the highest order of the derivative. So, here also we say is the order of the highest derivative is called the order of the equation. Say for example, del u over del x plus del u over del t is equal to 0. This has the derivative of the first order only. Similarly, u times del u over del x minus del u over del t, again both the derivatives of the first order only. E to the power x del u over del x plus 4 times del u over del t is equal to t. Again we are having all the derivatives occurring are of the first order only. So, the highest order of the derivative occurring are the first order, and in the second equation we do have the unknown function u also, but the derivative is only of the first order. So, all these are the examples of first order equations. Similarly, if we see other examples, del 2 over del t2 is equal to c square times del 2u over del x2. Here the derivative occurring is of the second order, this is also of second order. Del 2u over del x2 plus del 2u over del y2 is equal to 0. Here also the second order derivative, that the highest order derivative is occurring is the second order. In this also the highest order derivative which is occurring is of the second order. You remember that this is our one dimensional wave equation, this is two dimensional Laplace equation, this is two dimensional Poisson equation. The highest order derivative is occurring is of the second order. Similarly, in this one, this is two dimensional wave equation. So, we do have all these equations, the order of these equations is the second order. Next, the term is linear partial differential equation. As in the case of ordinary partial differential equations, we set it to be linear if the derivatives and the unknown functions are occurring linearly. So, similarly, here also we are defining linear partial differential equation. A partial differential equation is linear if it is of the first degree in unknown function and its partial derivative. Say for example, in our examples if we see this example del u upon del x is equal to del u upon del t, we are having is that the derivatives are occurring in the first degree and linearly. Here also the derivatives, that is second derivative, first derivative, all are occurring linearly. The coefficient is c square, c is a constant. Here also del 2u over del t2 is equal to c square del 2u over del x2. The coefficients is c square which is a constant, so they are occurring linearly. In this equation you see e to the power x del u over del x plus 4 times del u over del t is equal to t. The coefficient of del u upon del x is e to the power x. It is not a function, this is not containing u. Similarly, the coefficient of this is 4, on the right hand side this is t, this is not a u. So, we are having is that the unknown function and its derivatives, they are occurring linearly. So, this is also linear. Here also we see that derivative is the function the coefficient of the derivatives del u over del x, that is 1 by x, the derivative of this coefficient of this del 2u over del x2, that is the 1, del 2u over del t2, the coefficient is minus 1. We are having is that the coefficients are not having the function of u or the other derivatives of unknown function. So, this is also linear. So, all these are examples of linear. In partial differential equations, we will define some more kind of linear equations. One we call semi-linear. If all the derivatives of u occur linearly with coefficients depending only on x, We had seen in the last examples, that is, some where the coefficients were depending on x, some where the coefficients were depending on t. So, now if the coefficients are depending only on x, so when I am calling it x, it may have x, y or z depending upon if it is of higher dimensional equation. Then this equation is called semi-linear. Let us see some example of this one. If I take this example, del 2 u over del x 2 plus del 2 u over del y 2 is equal to f of x y. This is semi-linear. Here the you are having is that the coefficients, we are not talking about the other one, we are just talking about the coefficients of the unknown function and its derivative, they are constant here. Here also it is constant, and what we are having is, that is, here we are having is that the right hand side, that is the constant function, it is u, and a function of x and u, we are saying is that function is having u linearly and its coefficient is depending only on x, its coefficients are depending on, this may be a function of this one, but the coefficients would depend only on x. This is semi-linear one. Similarly, we would define one more kind of partial differential equation that we are calling quasi-linear partial differential equation. What it is? If all highest order derivatives, whatever be, if the second order or third order or first order, highest order we have to take in that equation, that occurs linearly with coefficients depending on x, u and lower order derivatives of u, then the equation is called quasi-linear. See, for example, del u over del t plus u times del u over del x is equal to 0. Here the unknown function is u, its highest derivative over here is of the first order, its coefficient is depending on x, u and lower order derivatives, because this is first order. So, there is no lower order derivative, unknown function u is there. So, here the derivative is here the coefficient is u. This we call quasi-linear differential equation. In ordinary differential equations, we had only linear differential equations, and there we said is, that is, if the coefficients are the constants or the coefficients are the function of x, there we have discussed only one particular case of coefficient of x, and that we called Cauchy equation. There also we have done something is called the homogeneous and non-homogeneous. In the similar manner, here also we define this particular equation is known as Invisit-Bharzar equation. Non-linear equation, let us see, if it is not linear, semi-linear or quasi-linear, we call it del u over del x square plus del u over del y whole square is equal to c square. You see, the derivative is del u over del x and del u over del y, and we are having its degree 2. So, they are not having degree 1. So, this is non-linear. This is the simplest example I was giving. Now, as in the ordinary differential equations, here for the linear partial differential equations, we again define the homogeneous and non-homogeneous. So, a linear partial differential equation is said to be homogeneous if each term of the equation contains either the unknown function or its derivatives, and otherwise the equation would be called non-homogeneous. What we mean by, if you do remember, there is when we have used in the ordinary differential equations the linear differential equations, we said is that all the derivatives and the unknown function were occurring linearly and the right hand side is 0, and if right hand side was not 0, we called it to be non-homogeneous. The same thing is being said here in the different manner, that is all, that is each term is containing either unknown function or its derivative, otherwise it is 0. So, a homogeneous equation example, del 2 u over del t 2 is equal to c square times del 2 u over del x 2. So, if I try to write in that manner in which we used to write the ordinary differential equations, we would write it as del 2 u over del t 2 minus c square times del 2 u over del x 2 is equal to 0. So, the right hand side would be 0. Similarly, del u over del t is equal to c square times del 2 u over del x 2, that is each term contains either the unknown function or its derivatives. We are not having any function, any term here which is not containing u or its derivatives. Non-homogeneous equation, you see, e to the power x del u over del x plus 4 times del u over del t is equal del u over it should be del t is equal to t. Now, you see, we are having this containing the derivative of unknown function, containing the derivative of unknown function, but this is the function, this is the term which is not containing, neither containing u nor its any derivative. So, this is non-homogeneous equation. Similarly, you see here this term is containing the derivative with respect to x, this is also containing the derivative with respect to x, this term is also containing the derivative with respect to t, but this term is not containing any of u or its derivatives, first order, second order, or with respect to x or t, anything. So, this is again a equation which is non-homogeneous. Now, as in the ordinary differential equations we defined the solution, we said is that differential equations are in unknown function u, that is the unknown quantity is a function u. So, here the solution would also be a function u. So, which function we would call the solution? The definition says a solution of a partial differential equation in some region R of the space of independent variables is function that has all the partial derivatives appearing in the equation in some domain containing R and satisfies the equation everywhere in R. Let us see, what we are saying is, if there is an equation, partial differential equation, that means it will contain the relationship between the unknown function and its derivatives with respect to certain coefficients. So, what we say is a function which is continuous and have all the partial derivatives which are appearing in that equation, that is, it must have all the partial derivatives of that function, and then that function and its derivatives must satisfy the equation everywhere in that region R, then we would call this a solution in that region R. Before seeing is that is what is the solution, let us revisit our partial differentiation a little bit, so that whatever the terms or whatever the partial derivatives we would be involving in our understanding of this partial differential equation. I am just giving you that little bit understanding over here. So, let us see it with the help of certain examples. Now, if my function u is of x and t, where function is of x square into sin t. Now, we do know that we could write its partial derivative with respect to x, that means we would treat t as constant and the derivative of x is 2 times x and sin t, that is as treated as constant. Similarly, if I want to find out the partial derivative with respect to t, I would get it as x square into cos t. Why this x is being treated here as a constant and the derivative of sin t is nothing but the cos t. Take the another example. If u is a function of x square plus t square whole square plus e to the power x, then what will be its partial derivative with respect to x and with respect to t. So, first let us take with respect to x. This was a function of x and t. So, we will just treat it as a chain rule or the function of function. So, 2 times x square plus t square and then the derivative of this would be 2x because t is treated as a constant, plus this is the derivative of e to the power x with respect to x is e to the power x. So, what we do get is finally 4 times x into x square plus t square plus e to the power x. Now, take the derivative with respect to t and treat x as a constant. Then del u over del t would be 2 times x square plus t square as a whole one, and then the derivative of this function would be only 2t because x has been treated as a constant, and since it is a constant, so the derivative will not occur here. So, what we get 4t times x square plus t square. Now, this is the we have used the here the chain rule of the ordinary derivatives. Now, for the partial derivatives, the chain rule says, that is, if u is a function of the two variables r and s, where both r and s are also the function of two variables, say x and t, that is, r is a function of x and t and s is also a function of x and t. Then if I want the derivative of u with respect to x and t, while u is actually a function of r and s, then the chain rule says that partial derivative of u with respect to x is can be given as del u over del r into del r over del x plus del u over del s into del s over del x. In the ordinary differentiation, what we had only one variable and then that was a function of another variable. So, we had it only du over dz and dz by dx. Now, here because it is of the two variables, so we are adding it up. If it is more than two variables, again we would go on this adding it up in that manner. Similarly, the partial derivative with respect to t can be given as the derivative of u with respect to r and then derivative of r with respect to t, all are the partial ones because r is also a function of x and t, and then the partial derivative of u with respect to s, that del u over del s, and the partial derivative of s with respect to t, that is del s over del t. Let us see one example. Suppose u is sine of r plus s square, where your r is t times e to the power x and s is x plus t. I want the partial derivative of u with respect to x and t. So, first the partial derivative of u with respect to r, del u over del r, that is cosine of r plus s square, and the derivative of r is 1, s has been treated constant. If I want the derivative with respect to s, then it would be cosine r plus s square, that is the derivative of sine r plus s square, and then the derivative of s square, that is 2s, and we would require actually the derivative of r and s with respect to t and x. So, derivative of r del r over del x, treating x as the variable and t as a constant, t times e to the power x. Similarly, del r over del t would be e to the power x, t is constant, derivative of t is 1, del s over del x would be 1 and del s over del t would be 1. So, using the chain rule, del u over del x as del u over del r into del r by del x plus del u over del s into del s over del x, we would get cos r plus s square into t to the power e x plus 2s cos r plus s square into 1. That we can rewrite it in this form. So, replacing my r and s by the function, that is r is t times e to the power x and s is x plus t. So, it is this one. Similarly, if I try to find it out, del u by del t, that would be del u by del r into del r by del t plus del u by del s into del s by del t. Now, substitute this del u by del r cos r plus s square, del r by del t was e to the power x, del u by del s is 2s cos r plus s square and del s by del t was 1. So, we would be getting this, again substituting this r and s square in the terms of x and t, we would get this one. So, this is what is your chain rule. Now, after this basic concepts revisiting, let us try to find out verification of solution to the partial differential equations. That is what we will try to see. Given certain partial differential equation, we will try to see if a given function is solution of it or not. That is what, why we will call it solution, if it is having those partial derivatives which are involved in that equation, and if that unknown function and its derivatives are satisfying that equation. So, let us take one example. Consider this first order wave equation. This is called the first order wave equation, c times del u over del x plus del u over del t is equal to 0, where this constant c is the constant and this is called the wave speed. Now, we see that is in ordinary differential equations what we had find it out, that is there was certain function which we said is that they are satisfying the equation, and we did find it out that the function was same with the constant change here. You see here actually what will happen, that is we would be having many functions which would be satisfying. Now, let us see that is with the example and then we would find it out. Let us see, take the function u as sine of x minus c t. The derivative, so we do know that is sine is a continuous and a differentiable function, and the derivative with respect to x and with respect to t both would be existing. So, we have here the first order derivatives. So, we do find out what is del u by del x, that would be cosine of x minus c t, and the derivative of x minus c t with respect to x would be 1, and derivative with respect to t, that is again cosine x minus c t, and the derivative of x minus c t with respect to t would be minus c. So, it is del u over del t is minus c times cosine x minus c t. So, now if you see c times del u over del x, what it would be, it is c times cosine x minus c t plus del u over del t, that is minus c times cosine x minus c t, that gives me 0, that is the equation is satisfied. That means, this is the solution to the equation c times del u over del x plus del u over del t is equal to 0. Now, you see what it is solution, how it is looking up. If I take c t to be 0, we have taken x minus c t. So, c t I have taken 0, or you could say is that is c I am taking as 1 and t as 0, then this would be the this function is solution to the given equation. If I take t is equal to 1, t is equal to pi by 4, I am getting is that the solution is little bit changing towards the right, shifting towards the right. The function is same, but it is shifting towards the right. You see at t is equal to pi by 2, it is shifting this one, 3 pi by 4, it is again more shifting, this is shifting. Let us see, that is what we have find it out. We are finding it out that at t is equal to 0, this is the function, at t is equal to pi by 4, this is the function, at t is equal to pi by 2, this is the function, at t is equal to pi by 3 pi by 4, this is the function, at t is equal to pi, this is the function. So, what we are having is that is my function, the shape of the function is same, but it is shifting towards its right as we are changing our c t. So, either you could say is that t we are keeping fixed and c we are changing, or you could say is rather it should be that is c is being fixed and t is changing, that is t as I said is we are treating it as a time. So, with the time this wave is shifting towards right. Now, let us take another function u as 1 minus x minus c t whole square in the range when x minus c t whole square is between 0 and 1 and it is 0 otherwise. Now, we see that this is also satisfying our wave equation. See what will be del u over del x? This function is actually we find it out that is continuous, but we find out that del u over del x in this region it is minus 2 times x minus c t, derivative of x is 1 and in this region it is 0. Similarly, the derivative with respect to t would be the derivative of c t would be minus c actually. So, we would be getting 2 times c x minus t in this region and 0. So, now if I consider our wave equation, that was c times del u over del x plus del u over del t. We see is that is what it is. If I multiply it with the c, these things are just c times del u over del x is same as minus del u over del t. In this region this is same, and in this region, that is when x minus c t is greater than 1, both are 0, so they are satisfying it for all x. That means, this is also a function, this function is also satisfying our wave equation. Let us see what this function is. This function is this one, when I am taking is Ct is equal to 0. That is from -1 to +1, this is a wave, this kind of curve, and then so if I move this Ct to 1, what I get is that function is shifted from 0 to 2. If I move it to 2, 1 to 3, it is moved with 2 to 4. Now you see the shape was not changing, the shape was exactly same from 0 to 1, but the function is shifting towards the right. You see this is with 0, 1, 2, 3 and 4. So what we are having is the shape is same, the only thing is that the wave, that is this wave which has been forming, that is same, but it is shifting as with respect to time, this is shifting towards its right. Now let us treat another one. Now here what I am taking is this function f of x minus Ct, where f is any arbitrary function. I am not giving any form of f. In previous two examples I had given that f as sine, and then f I have given as a particular function. Now here it is f is a general function. Now let us see whether if I treat this as a general function which is continuous and has partial derivative with respect to x and t, will it satisfy our wave equation? So use this chain rule, we get del u by del x as f dash x minus Ct and del u over del t as minus c times f dash. F dash means is, that is I am taking is the derivative with respect to z, that is x minus Ct. Now what we are getting is del u over del x is f dash z and del u over del t is minus c times f dash z, that is if I take c times f dash z, that is same as minus del u over del t. So this equation is satisfied. What I was requiring is that is f is continuous and has partial derivatives, are differentiable with respect to both this one. So this is also a solution. What it says, in ordinary differential equations, if you do remember, we were used to find out a solution which involves arbitrary constants. Now here what we are getting is, I am finding out a solution which is involving actually arbitrary function. That says is I do have in partial differential equations, my solutions may involve arbitrary functions. And how to determine this unique solution? Does this partial differential equation doesn't have a unique solution? Because we said is an ordinary differential equations, we do had unique solution, that there was general solution, then there was unique solutions. We said is that there would be unique solution which we could find out from the general solution, that is given particular values to the arbitrary constants. If we had used certain side conditions, what those side conditions? We said is that there were initial conditions. Initial conditions means if it is a first order equation, we said is initially, that is from where the function is starting, or if it is second order, we had two initial conditions. First was that is from where the function is starting, the second was that maybe that is at the first derivative is at the initial point. So we are having is that in ordinary differential equation we had initial conditions. For higher order in differential equations, say for nth order, we had n minus 1 1th derivative, we had got the initial conditions for all, that is n initial conditions. Moreover, we had learned there in the ordinary differential equations, that is other than the initial conditions, we were having the boundary conditions as well. When the function was defined on a certain finite region, we said is that on both the boundaries we had certain conditions imposed upon, and in the boundary, that those problems we called boundary value problems, and we had seen that is in the boundary value problems sometimes the solution was existing, sometimes the solution was not existing. Now in the similar manner here, to determine this unknown function f, we require some side conditions. So we call them some additional side conditions. They could be of the form of initial conditions, or they could be of the form of boundary conditions, or sometimes it is a combination of both. and so we are calling them as in the ordinary differential equation. If you do remember, we were calling with the initial conditions, if we are solving a problem, we called it initial value problem. So, here also we would call them initial value problem. With boundary conditions imposed upon, we call them boundary value problem. And when we are having the combination of both, that is, my partial differential equation may be having both the kind of side conditions, initial conditions as well as boundary conditions, and we call them initial and boundary value problem, or similar, or simply initial boundary value problems. Now, with these, if you do remember, in the boundary value problem in the ordinary differential equations, we had find it out with certain boundary conditions the solution is existing, and with certain boundary conditions the solution was not existing. While in initial value problems we find it out that is always the solution was existing and that solution was unique. Here again with these side conditions, whatever the conditions, that is the data is given, that is the function at initial value is some particular value or some particular function, actually here it would come out. We are saying is that those values is called data in this partial differential equation, and with respect to those data, if for some initial value problem or boundary value problem or initial boundary value problem, if unique solution is existing, because in boundary value problems in the ordinary differential equations we had find out that all the time solution was not existing. So, here what we would say, if with respect to these side conditions, whatever these side conditions are that we are calling the data, with respect to that data, if for any partial differential equation the unique solution is existing, we will call that problem as well posed problem, otherwise it is called ill posed problem. Now, so come back to our example, we had find out that is we were talking about the first order wave equation, and we had find out that is a general function f of x minus ct could be solution of that equation. Now, we want to find out unique solution. So, let us impose first the initial condition. What initial condition here it would be? We say at time t is equal to 0, the solution should be of the two variables u as x and t. So, we are saying is that t is equal to 0, u x is a function of x. Now, here f could be of any particular function. Now, in general I am taking suppose f is a known function, then u x t we had find out that the solution as f of x minus c t. Now, if I use t is equal to 0, what it would give? It would give me that is at t is equal to 0, here I would get u x 0, and here if I put t is equal to 0, I would get capital F of x. Now, this capital F of x is same as my initial condition says is u at x 0 is equal to f x, that says is this capital F x must be this known function f x. So, what we are saying is that this initial condition which set that function u x is a function of x with known function, my solution is actually turns out to be that function f itself. So, what would be my function, my solution? My solution would be f of x minus c t, that is with initial condition I would get the unique solution with reference to that initial condition, that is function known function. So, say for example, I take f x as e to the power minus x square, then what will be my solution? My solution u x t would be e to the power minus x minus c t whole square. Let us see, is it a solution to this our equation? If I take its derivative with respect to x, I would be getting it as e to the power minus x minus c t square into minus 2 times x minus c t, and the derivative with respect to t would be e to the power minus x minus c t square into 2 c times x minus c t. So, you can just check that this is satisfying ourselves. Actually, we had already shown that it is satisfying with any f. So, whatever this f I am keeping it would satisfy this solution. If I put t is equal to 0, I would get here e to the power minus x square, that is my initial condition is also satisfied. How this function is looking like? You see here again I have taken with different values of Ct. When Ct is 0, this is the function. When Ct is equal to 1, this is the function, and when Ct is equal to 2, this is third one is the function. When Ct is equal to 3, this is the function. Again we are getting is the shape of the function is same, that is this wave is same. The thing is that is it is changing towards or shifting towards right. So, this is a solution. So, solution what we are getting is that solution is unique solution we can get for one dimensional wave equation with initial condition, where initial condition is being posed at the time t is equal to 0, the unknown function takes form of a known function. So, the solution would be in the form of that known function, because the shape of the function is not changing, the function remains same, only thing is that with the time t it is changing its place, that is it is shifting towards the right here. Now, let us come to the first order partial differential equation. First order partial differential equation, I will take the simplest example of first order partial differential equation, del u over del t plus Cu times del u over del x is equal to 0. Cu, that is the coefficient of del u over del x, it may be a function of u also. Now, if this C of u is just a constant, that is it is not involving any unknown function or any x or t, it is just a constant, let us say C, then this equation is the equation just now we had seen, the one dimensional wave equation, del u over del t plus C times del u over del x is equal to 0. We see that this is first order, because the order is one only, it is linear, the derivatives are occurring linearly, the coefficient is constant, right hand side is 0, that is we are not having any term which is not involving u or its derivative. So, it is homogeneous linear partial differential equation. We had already seen that we had called it first order wave equation. With our examples for the solutions, we had seen that all the solutions, in general actually we had find out the solution f of x minus c t, and if I use this f to be different values of the function, different functions we had seen, we had always find it out that the solution of this is giving is that is a graph of a function which is shifting towards in all those examples we had that it was shifting towards its right, that is it is changing the place only, and that is why we do call it the transport equation also, because it is transporting the data. So, you see is that is why we are calling transporting. So, if we do have this equation, we see is that is if the function is my e to the power minus x square, it is shifting towards right, that is it is transporting the function towards its right, because at the speed what we are saying is it is transporting at the speed c, with the c speed it is transporting towards whatever be the c. Now, here c all the time I have taken it to be positive value. So, it is shifting towards the right. Now, how to find out the solution of this first order partial differential equations? We require to know that is what is the method. Before knowing this method, we had seen only one example of first order wave equation. Let us take one more example and see that is does this also has more than one function as its solution. Now, we see is that this is now not an this is also a homogeneous equation, a linear one. We do have del u over del t plus c times del u over del x minus u is equal to 0. Now, verify that function e to the power minus t f of x minus c t is a solution of this equation, where this f again you see this is an arbitrary function. So, I am not treating it as a general, I am treating now with the arbitrary function. So, the form of the solution we are taking here is e to the power minus t f of x minus c t. Let us try to see. We have been given the function as e to the power minus t f of x minus c t. We require the derivative with respect to x and with respect to t. So, first find out the derivative of this with respect to x and t. So, where this dash is denoting the derivative with respect to x minus c t. So, del u over del x would be e to the power minus t times f dash x minus c t, because the derivative of x minus c t with respect to x would be 1. Del u over del t would be e to the power minus t, first this function and then this f of x minus c t as such. Then the derivative of this with respect to t is that c times e to the power minus t f dash x minus c t. Dash means the derivative with respect to x minus c t. Now, if substitute in the given equation, the equation was del u over del t plus c times del u over del x minus u is equal to 0. What we have got, that e to the power minus t f of x minus c t minus c times e to the power minus t f dash x minus c t, this is what is my del u over del t, plus c times this one, c times e to the power minus t f dash x minus c t minus u is my e to the power minus t f times x minus c t. Now, you see this is cancelling this one, this is cancelling this one. So, I am getting it is equal to 0. So, that was satisfying the equation. Again what we have got is actually that f here is in this one f is arbitrary. Let us see one more example. Let us consider this semi-linear equation where the coefficient is x, x times del u over del x plus del u upon del t is equal to 0 for x positive. Now, we are verifying that is f of x times e to the power minus t is a solution where f is again any arbitrary function. Let us try to see it. We are been given that the function as f of x into e to the power minus t. So, this we will take as z and use the derivative with respect to x and t. Partial derivative with respect to x, it would be f dash x times e to the power minus t, and derivative of x times e to the power minus t with respect to x would be e to the power minus t. Dash means the derivative with respect to this whole function as one variable. Similarly, del u over del t is x times e to the power minus t f dash x of e to the power minus t. Now, substitute this in the given equation. Equation was x times del u over del x plus del u over del t. So, del u upon del x, x times this x times e to the power minus t f dash x times e to the power minus t, this is same as here this is with respect to t. So, it should be with minus sign actually, this e to the power minus t. So, it should be with minus sign. So, we do get it with minus is 0, that is it is also satisfying the equation. So, we had got that is not only that first order wave equation, but we had different kind of equations, all are the first order equations. We had find out that is the function f was arbitrary in all those things. But one more interesting thing did you observe here, when we had first order wave equation, my argument that was x minus c t, that is unknown function f, but the argument was x minus c t. And when I have taken the another one, there I was having is that my argument was different, and here also we were having some multiplication, that is e to the power minus t and times something like that one. When I have took this example of a semi-linear equation, I have got that f is of course unknown, but this form, this argument is x times e to the power minus t. What we had observed that in all these examples, the function remains unknown, and we had find out that with initial condition in the wave equations we had seen that that initial condition was deciding what should be my f. If initially at time t is equal to 0, I give that the solution is taking this particular form of the function, then my function is being decided from there, but the argument is changing now. It says is that in ordinary differential equations what we had that my solution was involving arbitrary constants. So, we tried to find out the solution in general with arbitrary constants, and then we using those side conditions we tried to find out the value of those arbitrary constants, and we call them the unique solution, and the solution with arbitrary constants we call them the general solution. Here what we are having is that is solution is involving arbitrary function, but in these three examples we had observed that argument of the function is changing. Now, the question comes is how to find out this argument. Is there any method which says is seeing the equation, can I obtain the argument, or what should be the argument of the function? Of course, arbitrary function, because the general solution we must get in the terms of arbitrary function, but that arbitrary function is with respect to some other functions, or the arguments are also functions. Can I determine those functions or those arguments? So, we have learned today what is called partial differential equation, certain basic concepts, definition of partial differential equations, certain concepts which we are using in the partial differential equations. They are more like ordinary differential equations, but somewhere we had changed according to the partial derivatives. We had learned some more concepts or more terms other than partial differential equations. We call some semi-linear equations, some quasi-linear equations. We had learned that solution of partial differential equations are having unknown function as in the form of arbitrary function. We had seen that in ordinary differential equation one function was defining or is giving the solution of differential equation. In that function we can only change with a constant, but here what we had find it out that the function itself could be arbitrary. We had seen that with certain side conditions, as in the ordinary differential equations we call them initial value problems or boundary value problems. Here also we can use certain side conditions to determine the function uniquely, and those we called initial value problems, boundary value problems, or we could call them initial and boundary value problems. Of course, we will come later on all these particular things, but the first thing which we had learned in the first order partial differential equations, that the function has to be arbitrary, that has to be determined from the side conditions. What we do, get that argument of that function is changing as the equation is changing. So, we would get the solution of the partial differential equation, that is try to find out the methods to find out the solution of partial differential equations. As first method we would learn about determining the argument of the arbitrary function. So, in the next lecture we will go how to solve the first order partial differential equations. So, today we would be closing the lecture here. The next lecture we will go for the solution of first order partial differential equations. Thank you.